historic government building, and this is where you can find the College of Education office. And as you can see here in front, we have one planter followed by the door of the undergraduate office, and then there is another planter followed by the door of the dean's office, another planter, door, and planter. And as you can see, obviously the planter and door are alternating. In calculus, we also have alternating series, and that is going to be the focus of today's video. Specifically, we are going to talk about the alternating series test. First, let us define an alternating series. It's a series whose terms are alternately positive and negative. You might wonder why the signs are alternating. Well, you can see here in the first example that the secret ingredient is -1. Remember that when -1 is raised to an odd exponent, we will get a negative answer. However, when -1 is raised to an even exponent, then we get a positive answer. Hence, with the presence of -1, we get alternating signs. If n is equal to 1, then we get 1 as the first term. If n is equal to 2, we will get -1/2 as the second term. Now we get 1/3, which is positive if n is equal to 3. Next term is -1/4, and that is when n is equal to 4, and this will go up to infinity. Take note later on that 1/n will be represented by b sub n. Here is another example of an alternating series, the summation of -1 raised to n multiplied by n/n plus 1, and ranges from 1 to infinity. In this series, the first term is -1/2. That's when n is equal to 1. The second term is positive 2/3. That's when n is equal to 2. The third term is -3/4. That's when n is equal to 3. Once again, we will be using b sub n to represent n/n plus 1. The b sub n that I was referring to a while ago is in fact a sequence, and we use that in the alternating series test, which states if the alternating series, the summation of -1 raised to n minus 1 times b sub n ranges from 1 to infinity, is equal to b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6 up to infinity, where b sub n is greater than 0 satisfies two conditions. The first one is that b sub n plus 1 is less than or equal to b sub n for all n, and the second one is the limit of b sub n is equal to 0 as n approaches to infinity. Then we have this conclusion: the series is convergent. Remember, b sub n must be positive. Also, it must be decreasing. Plus, you have to remember that the limit must be 0. All these three conditions must be satisfied for us to conclude that the series is convergent. Moving on, we can make use of this illustration for us to have an intuitive idea that the alternating series is convergent. For this series, the first term is 1. That's the value when n is equal to 1. And so, the first partial sum, represented by s sub 1, is also 1. The second term is -1/2. We get it when n is equal to 2. Now, the partial sum s sub 2 is going to be 1 minus 1/2, and that is equal to 1/2. The third term is positive 1/3. So what's the partial sum? That's going to be s sub 3, 1 minus 1/2 plus 1/3. That is equal to 5/6. Next term is -1/4. So again, if we will have to get the partial sum, 1 minus 1/2 plus 1/3 minus 1/4, we get s sub 4, which is going to be equal to 7/12. If we have to continue taking the partial sums, the sums will have to converge to S. So this illustration is actually helpful for us to have an idea that indeed an alternating series, when having those conditions satisfied, is going to be convergent. It's time for an example. Let's consider this series. First, for us to establish that this is convergent, we need to show that b sub n is positive. In this series, b sub n is equal to 1 over n. This is fairly easy to establish that 1 over n is positive. We may begin our argument by stating that n is positive. So since n is greater than 0, b sub n is greater than 0. Next, we need to establish that b sub n is decreasing. So we need to show that b sub n plus 1 is less than or equal to b sub n for all n. So what is b sub n plus 1? That is simply 1 over n plus 1. And of course, we know that we need to show that it must be less than or equal to b sub n, which is simply 1 over n. We may focus on the denominator of the fraction. So we write since n plus 1 is greater than or equal to n. This is obvious because we just added 1 to n on the left side. And then we conclude hence 1 over n plus 1 is less than or equal to 1 over n. That is true for all n. Observe that we reverse the direction of the inequality, and that is because the fraction's value becomes less if the denominator becomes larger. And the last one, we need to show that limit is 0. So we write limit of 1 over n as n approaches to infinity. Well, this is in fact equal to 0. We don't need to make a lot of arguments because this has been established already. So we now make a conclusion that the series is convergent. Yay! So we're done with the alternating series test. Now you might wonder, if the limit is not 0, will the series be divergent? If you want to know the answer to that question, you have to watch the video that I made about divergence test. The link is provided in the description below. I'll see you at Gabaldon Building soon. Stay safe, everyone.